Alright, related rates. The first thing they suggest that you do is to, we're going to be able to do applications of some of the derivative rules that we've been talking about. The first thing they suggest is when you read a word problem is you want to draw a figure and label it. A lot of times that helps. The second thing is identify the rates of change that are known and unknown. The third suggestion is to find an equation that relates to quantities, especially keeping in mind of the one to be found. Differentiate both sides with respect to time and solve for the unknown value, and then evaluate at appropriate points in given situations. So that's just kind of a blanket step-by-step process for each case. So we'll go through these different types of problems and pick and choose the ones that are applied to this. So the first one is just a given equation. It's x squared plus 4y squared equals 25. They tell us that the value of x is 3, y is 2. dy dt, that's the derivative of y with respect to time, is negative 2 units per minute. That's all the given information. And then they tell us to find dx dt. Okay, so the first thing we're going to do is we're going to take our equation that's given. So we'll have x squared plus 4y squared equals 25. Now the image out to the right, I had this drawn ahead of time. You can either use a graphing calculator. It's basically or like Desmos is an app that you can use. Use your graphing calculator to give you a sketch of it. Sometimes the visual helps you, but in this case, this is what we're going to work with, and we're going to differentiate with respect to time. So we're going to take our given equation, and we're going to take d dt of each of the terms. So that's x squared. We're going to differentiate with respect to time here of our 4y squared all the way across. Okay, with that in mind, let's go ahead and do this first one. What is the derivative of that term of x squared? 2x, but what do we have? That's d dt, so 2x dx dt. Right? Plus, now let's do this term. What's the derivative with respect to time of 4y squared? 8y dy dt. Good. What's the derivative of a constant? 0. Alright, so now we're keeping in mind, we've differentiated. Next it says solve for our given. What are we looking for? Dx dt. So basically we want to move everything that doesn't have a dx dt with it to the other side. So I'm just going to bring down 2x and move the other term to the other side. Okay, solving for dx dt, what do we do? Divide both sides by 2x, good. So we will find out that dx dt, let's simplify that, it's just going to be negative 4y over x. Okay, so that's the equation that represents that. What about other given information? What else do we know? We know the values of dy dt. We also know the values of x and y. So at this point, we're going to substitute in all of our given values. So we have negative 4. What is y? Let me change this to a different color. 2. Good. What about x? 3. And what about dy dt? Negative 2, right? Okay, we can simplify that and we'll get dx dt, which is what they ask us to find, is going to be 16 over 3 units per minute. Someone want to let her in? Oh, it's open. Oh, the one that was in 227. I think so. It's over right there. If not, I'll come. Alright. So we're going to do a similar thing with this next one. Actually, if you want to go ahead and try this one on your own, you can. So go ahead and take a minute. They give you all the given. The sketch is not provided. Now, I put that on here just to save us some time. And I'm usually not very good at sketching on the spot, so I try to give a little bit neater version of it. So there you have everything that's given except for the sketch. Now you can pull that up on your graphing calculator or just make an XY table and sketch that yourself. But go ahead and use the same processes that we did in number 1 and calculate dx dt for number 2. Okay, so we're going to check our work on this. You can see this one was a very basic one. Take the derivative with respect to time of all the terms, and so we'll get dx dt. Here you're just going to get 8y dy dt, and then when we're substituting values in here, we have 8. Our y value was given to us as a 1, and our dy dt is -1. And we solve this to be, so the rate that the x value is moving with respect to time is going to be -8 units per minute. Okay, so this next one we have a cube's surface area is increasing at a rate of 75 centimeters squared per second. And at what rate is the cube's volume changing when the length of each side is x equals 2 centimeters? We're going to let x be the length of each side of the cube, and given x equals 2 centimeters, find your dv dt. So we're looking for the rate at which the volume is changing. So we want to find dv dt. Volumes change with respect to time. Now I went ahead and sketched this. This sketch was not provided, so sketch that, and then we'll go from there. So I'll give you a minute to do that. Alright, so there's no particular way necessary. There's a lot of things that we're going to need to be able to find to solve this problem. But initially, what is our ultimate objective? To find dv dt. So we're going to obviously start with the volume. How would you represent the volume of this? What would be our formula? Volume is equal to x cubed, so length times width times height, right? So in this particular case, it would be x times x times x, which is x cubed. Now, that's our volume formula. We want to differentiate this with respect to time. So we're going to take d dt of each term, the derivative with respect to time. Okay, over here, that's just going to give us 1 dv dt. This should be x cubed. Alright, what about the right hand side? What will we get? 3x squared. Good, dx dt. Alright, now at this point we know ultimately we want to do that, but we don't know the dx dt term. Okay, we're not quite sure what that is, so let's go off to the side and use some of our other given information. We're going to hold right here. Ultimately, we're going to come back and use some information, but we need to go look to the other side. What other information was given in our problem? Let me go back up somewhere we can see a little bit of it. Surface area. Surface area is increasing. So if we take our surface area for this particular problem, area is going to be, what would that be? What's the area of, let's say, this side that I have shaded? X times x, right? Which is x squared, but that's only the surface of one of my sides. How many sides would we have for a cube? 6. So we would say area is going to be 6x squared for this particular case. Okay. They gave us values for dAdt, so we can see that we'll be able to use dAdt in a minute. So let's differentiate the area with respect to time as well. So let's do alright, so what will we get on our left? dAdt is just 1 dAdt. And on the right side, what do we get? 12x dx dt. Okay, now I noticed that over here I have dx dt, so if I was to solve this term for dx dt, I could probably find out some information. I could plug in some values there. So what could I do over here to get dx dt by itself? Divide both sides by 12x or multiply by 1 over 12x. Let me change color. So surface area. So this is just going to be our okay, so now we can plug that value in over here. So let's take our dx dt, this information here, and we can come now and substitute to continue on. So we'll have 3x squared over here, so dv dt, 3x squared, and then we'll plug in 1 over 12x dA dt. Okay, at this point we can simplify a lot of things. We're given values for x. We know what x is because what is x in our given problem? 2 centimeters, okay? Also, we also know something else. We also know that dA dt was given. dA dt was given, so we can plug in all those values. So in this next step, let's plug in all the knowns that were given. So we have 3x squared, so our x was 2 centimeters, so we'll have 3 times that. And then we also have 12x we said was 2 times, and the ADT was 75 centimeters squared per second. So go ahead and simplify that to find our dBdt. .5 centimeters cubed for the volume per second.